Hello everyone, my name is Aurore Blelly and I am a PhD student at CEA Saclay in France. Today, I'm going to present you the Sparse data inpainting method that I've been developing with Jérôme Bobin and Hervé Moutarde to deal with data gaps in LISA. In this talk, I will mainly focus on galactic binary gravitational waves as GBs represent millions of expected sources, among which we hope to identify only a few thousands. As they have a rather low signal-to-noise ratio, in order to identify them properly, these sources need to be observed continuously for a long-duration observation. This need for a continuous observation over a long time period conflicts with the fact that there will be recurrent, scheduled and unscheduled measurement interruptions. And this will impact LISA science, as it will induce a leakage from information to noise. In order to illustrate this leakage problem, I represented here the Fourier transform of a non-gapped signal in red and the Fourier transform of the same signal with gaps in green. The presence of gaps in time-dependent signals lead to a distortion of the noise spectrum in Fourier domain. Now, if we zoom on the part where signals are indeed present, we can see that frequency peaks that were visible when there were no data gaps are now completely drowned in the noise. We should not be able to observe them anymore. Palliating this problem requires limiting the leakage between estimated noise and signal. For that purpose, it is essential to distinguish signal and noise. This is the reason why we developed the Sparse data inpainting method. Our objective now is to mitigate the impact of gaps in LISA data by filling the gaps by making use of as little new information as possible. To our knowledge, there is only one other method that was developed to tackle this problem, which is the data augmentation method. It proposes a way to fill the gaps with random noise thanks to a sampling process and a Markov chain Monte Carlo algorithm for source identification. But so far, it has only been tested with a small number of sources. We decided to adopt a different strategy. Instead of going for identification using a parametric description of the waveform, we directly exploit its structure as it is really well known. Not many studies have been so far dedicated to gaps in LISA, but we already know that there will be many to come. What is the impact of gaps on LISA science? How can we deal with them? Is there a best scheduling strategy for maintenance gaps? We will not provide a definite answer today, but we will bring some new elements to this discussion. We developed the Sparse data inpainting method with galactic binaries in mind, as they are the sources present in greatest proportion among all observed sources. We expect thousands of GBs to be identifiable, and for this type of sources, the waveform is known quite precisely. On the right, I represented the expected waveform for a channel, both in time domain on the top and frequency domain on the bottom. Several observations can be done. First, the waveform is essentially monofrequency in Fourier domain. Thus, it can be approximated by only a few Fourier coefficients, which means that they have a sparse representation in Fourier basis. Finally, contrary to the signal, the expected noise does not have any structure neither in time domain nor in frequency domain, but we know its expected distribution in the case where there are no gaps. However, when the data is gapped, it impacts both the structure of the observed waveform and the effective noise distribution. From now on, we will rely on three main hypotheses. The first one is the structure hypothesis. The expected signal, for GBs, is supposed to have a sparse representation in Fourier basis. The second is the noise hypothesis. Here, we expect the noise to have a Gaussian distribution with non-power spectral density in frequency domain. The third hypothesis is the prior knowledge of the time location of gaps. Thus, we can represent the presence of gaps by a mask function which value is 1 at a time t if there is no gap and 0 otherwise. Our goal is to jointly estimate the ungapped signal as the sum of all sources and the noise as the minimizer of a cost function judiciously chosen. The signal and the noise will be chosen so that their sum matches with the observed data y outside of the gaps. They have to minimize a cost function composed of a first term constraining the solution to be sparse in Fourier basis, and a second term constraining the noise level in Fourier domain with regard to the expected power spectral density. The sparsity term is based on a threshold gamma that is automatically chosen according to a rejection rate set with regard to noise level. As for the resolution, it alternates between noise estimation and signal estimation until convergence is reached, which is possible because the cost function is separable in each variable signal and noise. The convergence speed can vary depending on the gap size and frequency. Let's now take a look at the resolution process. As I explained before, the algorithm will alternate between estimating the noise in the gaps and estimating the global signal. We first initialize the algorithm. Since we do not have any information on the signal, we set it to 0. Now the input data looks like that. It is a gaps time series that is the sum of the source signal, here represented in dashed black line, and the noise. One algorithm iteration is now divided into 4 steps, which are the computation of noise out of gaps, the estimation of noise in the gaps, the computation of the inpainted data, and signal estimation. The first step is computing the noise out of the gaps. This is simply done by subtracting the signal estimated at the previous iteration from the measurement y. This is the type of data we will work with. We subtracted an important part of the signal, so only the noise and some signal residual are left. The second step is the noise inpainting step. We estimate the noise in the gaps with regard to the noise we computed out of the gaps. The missing noise is computed so that it minimizes the overall noise level with regard to the expected noise distribution. This means that the noise out of the gaps is the one computed at the previous step, and the noise in the gaps is computed according to it so that the Fourier spectrum can be flattened. The third step is data inpainting. It consists in updating the observed data with noise and signal within the gaps. More precisely, taking the measurements, we add in gaps only the noise that we just computed and the signal we estimated at previous iteration. The last step is the signal global estimation. We consider the inpainted data as a non-gapped data. We then solve a denoising problem aiming at estimating the sum of signals coming from galactic binaries. This process is described in details in an archive preprint, and the corresponding code is available on GitHub. So this would be the input data, and after denoising, we find that a good approximation of the sum of signals is given by the dashed blue plots. Now, we repeat this iteration until the algorithm converges, which is usually quite fast. It only requires a few iterations. We tested our algorithm on LDC13 data, that were the 10 verification binaries, with Gaussian noise. We simulated 2 types of gaps. For maintenance planned gaps, we chose 7 hours gaps once every 2 weeks. To simulate unplanned gaps, due to glitches for instance, we took 10-minute gaps once every day. On the plot, I represented in green the Fourier transform of the gaps data, and in red the Fourier transform of the corresponding inpainted data. We observed that the effective power spectral density was indeed flattened, and that the signals that were previously drowned in the noise in the green plot are now totally visible on the red plot. And this result is even really close to the one that we would observe without any gaps. This means that we successfully limited the noise leakage thanks to the data inpainting process. This process is all the more successful that the extracted signal corresponds exactly to the one produced by the galactic binaries. So we tried our algorithm on a set of data a bit more challenging, a set of 100 waveforms that were randomly chosen. The data inpainting algorithm could flatten the effective noise power spectral density as efficiently as it did for 10 galactic binaries. More specifically, the whole algorithm worked at the same speed with 10 times more sources than before and could handle without any problem the data inpainting. So as a conclusion, we propose a new non-parametric method to mitigate data gaps in LISA. This method enables us to do an efficient reconstruction of the signal and the noise in the gaps. And this is rather fast, as it takes less than 2 hours to process for 2 years of data on my laptop. It can work with a large number of sources, and the framework around it is really flexible, as it can be adapted in numerous of cases. First, for instance, for power spectral density estimation, as the noise distribution may not be known initially. We already tested it and it works really well. Second, for another source type, by only choosing the base in which the waveform has a sparse representation. And last, for mixed source type, by choosing one adapted base for each source type. Our next project concerning this method is to run an extensive testing in order to assess the impact of gaps on signal restitution. Thank you for your attention. If you have any question, please ask them in the feedback section or send me an email. Thank you very much. Goodbye.